All right. So if you've been in the last talk, welcome back. I'm still here. I'm still around. So this is now joint work with my other PhD student that I brought, Marius, and we will be talking about why you should not trust the locals, in particular local storage and cookies and things like that. And I'll try to make a case for why you should not call it reflected persistent at DOM XSS. But more on this in a second. So first off, who are we? So again, I'm Ben. Hi. I work at CISPA. I had the Secure Web Engineering, Secure Web Applications group, sorry. And this is Marius, PhD student since October 2018. Still first year PhD student, yes, very young and fresh, how he looks. And so this talk is about XSS. And so if you even look at the XSS cheat sheet on OWASP, you'll find something like this. Also, if you open a textbook, it will tell you there are 3 different types of cross-site scripting. There is reflected cross-site scripting, exemplified here in PHP on the left-hand side. You just have a get parameter and just echo that back, right? Obviously in XSS. You have persistent XSS where you on the server side have some persistence mechanism, be it a SQL database, be it a NoSQL database, or just files or whatever, just persistent storage. And then you have what most people call DOM-based XSS. And so essentially this is JavaScript code that is insecure. So here we have document write location hash slice 1, assuming that the browser does not automatically escape the hash. Fortunately, most of the browsers do it today, but Edge is still vulnerable in this case. But this is essentially, if you look at the amount of code and the syntax somehow, it looks a lot like the left-hand example, right? So document writer echo it's virtually the same, and then you just take some part of the URL and echo this back. And so I'd like to make a case that this is actually not sufficient to have these 3 types of XSS, but rather we have to think about this in terms of 2 dimensions. And that is namely whether it's reflected or persistent, or it's caused on the server side or on the client side. And so what you've added here in the lower right-hand side corner is the fact that we now also have persistent storage on the client, right? We have always had cookies. But importantly, since a couple of years, we have local storage. And local storage is meant to store larger amounts of data. Cookies are very much bound. And so in this case, we see that we first have a data flow where we have a set item with something that is attacker controllable, so the location hash. And then this thing is later on used to retrieve something from the local storage, from the persistent storage, and write it into the document. And so if you take nothing else from this talk, then please at least remember to not call it DOM XSS anymore, if you may. So let's first talk about the different types of persistence mechanisms and also of sinks that we consider for our work and that we think are important to discuss here. So I said already before, we've had cookies for a while. Cookies were not meant to store data in that sense. They were mostly used to store, session identifiers, or preferences like languages and so on. So they have a very limited character set. So you can, for example, not use a semicolon in a cookie because that's the separator between cookies. And it's also bound to be at most 4K characters. Cookies are bound to an ETLD+1, so a registerable domain, or even a host name if you want to. So that means that foo.bank.com running over HTTP can actually set a cookie for its parent domain, bank.com, which will be sent to HTTPS bank.com as well. And it will also be sent, in this case, to the subdomain of bar.bank.com. And so how can this go wrong? Something like this. So we have a username that we're getting from the cookie. Then we get here the get element by ID logout. And assuming that I have, as the attacker, and Marius will tell you about how this will work later on, I have compromised this cookie somehow. So I've manipulated it in my victim's machine. I have a clear XSS here, right? So essentially, we're taking a string that is attacker controllable. That's the assumption, the cookie, and we're sticking it here into this username. So obvious XSS again. The second thing is, as I said before, web storage. Web storage actually comes in 2 different fashions. So there is session storage and local storage. We'll not talk about session storage because that's storage that is only bound to a specific window. And if you close that window, it's gone. So it's not really persistent in that sense. Whereas local storage is persistent and shared across all sites of the same origin. As I said, it's bound to an origin, so that means that if you modify the local storage of HTTPS foo.bank.com, then that value is also only there for HTTPS foo.bank.com, which is important for later on in our attacker models. And then this is a second sink that we consider for client-side XSS. which is eval, right? Everybody knows that eval is evil. And you'd say, this is a made-up example, right? Nobody would use local storage for code caching. I'll leave it to Marius to tell you more about this later on. But essentially the idea here is that you have something stored in local storage, and then you just evaluate that. And a third type of data source that we looked at, or persistence mechanism, is IndexedDB. So if anybody has used IndexedDB, I'm very sorry for you, let me put it this way. It's meant to be a NoSQL database, especially also shared with service workers. So in this whole progressive web app hype that has been going on, we have different concepts: database, object stores, transactions. But the gist of it is, if you want to retrieve a single value from IndexedDB, you need about 30 lines of code. Okay, so that's a lot of fun. It's also bound to an origin similar to local storage. And so I've avoided putting these 30 lines of boilerplate code here, but let's just assume that there's a function which is called getIDB_entry, and it will return of the database, and its object store the value proto. And so if we use that, and it's controllable by an attacker, then also this script can go horribly wrong in terms of XSS. What are we doing? We're creating a script element, and then we are assigning the source property of the script element with proto, which we assume is controllable by an attacker. So I can just put kittenpix.org there, or gps-kittenpix.org, and in this case, then this content will be loaded from my page and not the intended site. And so now that you have some background knowledge about sources and sinks, I actually let Marius take over and talk a little bit about how we can find now XSS in the wild.
Yeah, so thanks, Ben, for bringing us all up to speed of what we're actually trying to investigate. And if you have attended some of the other talks talking about XSS and also followed what Ben was just telling you about different kind of sources and some sinks which then lead to code execution, also having Freddy's talk in which he make use of linters to actually find such assignments to dangerous sinks, we're essentially doing a similar thing. So we want to track data coming from these and ending up in a dangerous sink. But contrary to what was shown before, we're doing this dynamically. So we're building upon research that Ben actually has done during his PhD, where we built a Chromium, patched it such that it has taint tracking in it, such that we can really have a byte level taint tracking of these values, which originate from these different client-side stores and end up in the code executing sinks. Now, in this image, what you can actually see is that we have only cookies and local storage, and that has a simple technical issue. So we cannot actually track IndexedDB with that taint engine, simply because in 2013, when that thing was built, IndexedDB wasn't so hot around then, and it just wasn't available in the engine. So, but we still wanted to have a look at how IndexedDB actually factors in the setting of persistent client-side cross-site scripting, which is why we actually did a second analysis, which is a little bit more simplistic in nature, and it has the concept or it embraces the concept of duck typing, and you probably know that. So if something walks like a duck and then quacks like a duck, it's a duck. And essentially what we're doing is we're looking in IndexedDB, and if it looks like code, so like JavaScript or HTML code, then we just try to substitute it and see where we can get with that. But more on that later. So for the next couple of minutes, we'll actually focus on our first analysis, so the one where we make use of the tainted Chromium. So let's start out with actually the collection of these data flows. So we make use of the tainted Chromium, run it on some web pages, collect data flows, and such things might look like it is displayed on the page. So we have some item either in cookies or local storage. So in that case, it's with the key user ID and the value foo. And we have recorded the data flow, which you can see is exhibited by this script. So let me just quickly walk you through it. So there is an item being retrieved from local storage with the key user ID, and then later on it's used inside an eval call. And with this information, so we have a data flow which we can track. So we have a call to eval with tainted data, and we know where that data is coming from, namely from a storage. What we can now do is go to the second step of our analysis and build an exploit candidate. Now what this means is we look at where the value is exactly being used within the string that is passed to the dangerous sink, and we automatically generate an exploit candidate that breaks out of the existing context and then executes a payload that we want to. And if we look at an example, it instantly becomes a lot more clear. So if we look at where we have the injection point, we can see that we are in an assignment to here the variable user with a single quote. So what we first have to do is break out of the existing context. That means we add like a single tick there. We also add a semicolon to end the statement. Then we can add an arbitrary payload, which is in this case just alerting XSS. And then if you pay close attention, we still have to take care of this quote here. So we just add a comment to take care of that. And this like magic gears in the middle, this is open source. We put that in GitHub. And also just recently we have also released the tainted Chromium engine. So, but you'll find more on that on the last slide. So having such an exploit candidate does not yet mean that we have found actually a cross-site scripting vulnerability. And that is simply because if we change something in the browser, a data flow can also be changed. So if there is a routine which checks that the value stored in one of these stores has a certain structure, and now we change the structure, the data flow might just not happen. This is why we need to validate that our candidates actually work in browsers. So essentially we just visit the web application, let it all fill up all the storages and all the caches, and then we just substitute our candidate into the storage mechanism and reload the page. If our payload survives the reload and the same data flow happens, we have our payload execute. And with this, we have like this automated pipeline where we can visit pages, collect data flows, build exploit candidates, and also verify that these are real vulnerabilities in web applications. And with this, we are basically set. So now we can start turning to like exploiting web applications at scale. And that's what we did. So we did an empirical study. We visited the top 5,000 domains. We found that around 2,000 of those make use of data which comes from one of these client-side stores somewhere within their application. So it might end up in the DOM, for example, with 1,600 from cookies and 940 of those from local storage. And the interesting part is that we found 418 domains which were susceptible to an exploitable data flow. So 418 are susceptible to, if an attacker can control one of these storage entries, they have a persistent code execution inside the victim's browser. What is interesting is that 13% of the cookie flows which we had were exploitable and 24% of the local storage flows. So local storage is really, in a sense, trusted by developers. And in general, we can see that developers really put trust into the integrity of these client-side storage mechanisms. And so in essence, they think that whatever they put in there is also the same value which they later on retrieve. And this might not necessarily be the case. But we did not only want to kind of find these bugs, but also find the root causes of those. So why are people even making use of these persistent values in the first place? And what we did was essentially looking at all our exploits, trying to find patterns and see what developers essentially wanted to do with them. And we found 4 categories. The first one being just some textual stuff which should be displayed somewhere in the DOM. So for example, they have some string and they just pass it to inner HTML, something of these sorts. This was the biggest category with around 214 domains. And there was no structure, no nothing. Another big category which we found was actually the storage of structured data. And this was the case for 108 domains. So they stored JSON or JavaScript stringified objects inside these stores, and later on just put them into eval. The next big category which we could find was code caching. So Ben already hinted at in the example. So the developers just put some HTML or JavaScript code inside into the store, and then later on just retrieved it, put it into eval or directly in HTML. And the last category, which was a little bit more like, we didn't expect that, to be honest. So there was lots of sites which stored configuration information. And what do we mean with configuration information? In this case, it's just simply host names from which further scripting resources should be fetched from. So essentially just doing some sort of client-side load balancing. At least that's what we suspect. But you have now bear with me for a longer period of time, while I didn't really tell you anything about the threat model. So you might ask yourself, so yeah, tampering with client-side storages, that is a really, really strong attacker model. That might be the case if you give me access to your computer and let me use your computer to Facebook, and I sneak up and open the developer tools and just put in some local storage entries or some cookies. But that's not really like a realistic threat model which we normally consider in the area of web security. And that's why we'll now talk about more like well-known attacker models, so say network and web attackers. But first, let's see of what we actually are trying to achieve. So we actually want to have an infection vector, so somehow an attacker can tamper with these storages, and then later on he has the added benefit of having a persistent code execution on the client side. And for that, like again, a single infection is sufficient, and that the benefit is you can mine bitcoins forever in the user's browser. Or you can plant keyloggers if, for example, session information is not accessible via JavaScript and you need to fish for credentials. And the first attacker model which we consider for that is actually the network attacker. And the network attacker is, again, as usual, sits somewhere in the wire, or maybe hosts an open Wi-Fi, and just listens and modifies HTTP traffic. In this case, the user is visiting some kitten pictures website, so Sebastian already introduced to our group's liking of cat pictures, and the network attacker sits on the wire, intercepts that request, modifies the response a little bit to also include a hidden iframe pointing to the site that the attacker wants to target. In this case, that's bank.com. The resource naturally being pointed again to HTTP such that the attacker can intercept the subsequent request and then add some script which then tampers with one of the storages. So either sets cookies or like plants, for example, values in the HTTP version of local storage. Again, remember that so for local storage, bound to an origin means that the attacker in this case can also only tamper with the HTTP version of the local storage. However, for cookies, as Ben pointed out, that's a little bit different, and the attacker has more capabilities there. Now, there might be one security mechanism which prevents the attacker from actually doing that, and it's called HSTS. It's a cool mechanism, HTTP strict transport security. We've heard it in the questions just earlier. And what this essentially does is it, once deployed by bank.com, is a mechanism which is a trust on first use mechanism. So it instructs the browser to only ever visit bank.com via HTTPS ever again. So completely eradicating the threat that an attacker can intercept HTTP traffic on that site. Now there's one small caveat, namely that a sound deployment of HSTS needs to include subdomains flag, because otherwise the attacker can just simply point it to a non-existing subdomain of bank.com and still do cookie shenanigans, because you can set cookies from subdomains to parent domains. So having essentially the same attack vector. Now, this does not work for local storage because it's bound to an origin. Now, having talked about our first attacker model, let's talk about the second one, so the web attacker. Now, the web attacker, as usual, hosts cat pictures, and in the background tries to like tamper with the user's browser. In this case, our web attacker actually uses another form of cross-site scripting, so a reflected variant of cross-site scripting, to get code execution and thus again plant a payload in the specific origin where he has the code execution, or for cookies again being able to do it for the registerable domain. And with this information, we can now start looking at which of the applications have both are both susceptible to one of these infection vectors, and then later on have a persistent XSS to find end-to-end exploitability. And that's what we did. And we have our two attacker models again. And we find that 290 domains are susceptible to end-to-end exploitability by our network attacker, either because they completely lacked HTTPS adoption, or they had HTTPS, they had HSTS, but simply forgot to have the include subdomains flag. Now for the web attacker, we used the very same engine to scan for reflected client-side XSS, and there we found 65 sites having both a reflected client-side and a persistent client-side XSS. Now, obviously, these are lower bounds because we only scan for that particular type of XSS. And if you trust the reports, I think it's Whitehead security reports, which indicate that every third application has an XSS, this is a lot more severe. And also thinking about you only need an XSS once in your lifetime if you have a persistent XSS to have an attacker plant the payload persistently in your web application. And let's be honest, at some point, a web application will have an XSS. And that way, this is the infection vector where the attacker can permanently get a foothold in your application. And now I'll actually like to show you a little demo of how such an end-to-end exploitation might look like. So what we're just first doing is clearing all the client-side storages. And you might wonder why we're using Edge in this case, because we use an XSS which still makes use of the old encoding behavior, such that the hash is not encoded, which is only present now in Edge. And what the first thing which we're doing is just visiting the target application, which is a Chinese single sign-on provider. And it's a little bit slow, but just such that you get a feel on how this site looks and feels. Just a normal web application. Now we're also closing the tabs such we don't make any cross-origin exploitations or something like that, and visit the attacker's page. And in this case, we are using a reflected client-side XSS to plant the payload. You can see that there is an iframe. There are some weird tags there, so we just inject something and the site doesn't look as nice. And now importantly, we close all the browser. So there's no JavaScript running, nothing. And the user might now switch to like the home network, or some time may pass before the user visits the web application again. And now we visit it again. And what we've now done is planted the payload. Our payload injected a keylogging functionality. And in this way, we'll soon alert the credentials of the user. But naturally, this could be anything. So you can send the credentials to your server, and also just like obviously be a little bit more stealthy than we are here. And I promised you that we are also having a look at IndexedDB exploitability, and that's what we are going to do now. So really a stupid analysis. And we looked at the top 10,000 sites this time. And interestingly, we found that 1,400 actually use IndexedDB. That was pretty surprising to us. But if we have a look a little bit more closely, we found that 470 actually really didn't make use of IndexedDB at all. But we suspect that they just make use of it for fingerprinting purposes to have one more bit of entropy to see if the browser actually supports IndexedDB. And of the rest of those, most of them used it through third-party code, which again underlines that IndexedDB is a pain to use. So as already hinted at, we looked at entries which resemble a JavaScript code, so parse it as JavaScript, see if there's an error. If not, nice, we found JavaScript code. And also just parse it for HTML, look for tags, and if there are tags, just substitute some HTML payload in there. And just if we have looked at what we found with the Taint engine, we found 100 cases where there were client-side code caching. And this gives us already a pretty good feeling that we'll probably find something here. And indeed, we found 80 sites which had a flow originating from IndexedDB going into like a sink. But of our exploit candidates, 60 out of 80 actually worked. So with this really stupid analysis, we found 60 sites which are susceptible to persistent client-side XSS. And this really underlines that this is a real threat in applications, and an attacker doesn't even have to have the sophisticated machinery, but just can simply look if something resembles code. But since we're not only here to tell you that the web is like totally screwed up, because that's what you probably already all know, we also want to kind of advocate and tell you a little bit of what we found in the wild and how you might actually do better. And that's what Ben's now going to present to you in the rest of this talk.
All right, thank you so much until here. So let's briefly go back to a slide that Marius showed before, and that is what type of data was being stored in the storages, and that was exploitable. And essentially, he said in the beginning, unstructured data. So this might, for example, be a username, right? This is a string, not meant to be code, and all these other things as well. So the question is now, how can we, like looking at the applications that we saw, how could we have secured them even in the presence of well, an adversary that is able of tampering with these local storages. So essentially, how can we protect our applications properly? And I want to go one by one through these use cases and give you a feeling of like, this is how things go wrong, how oftentimes trivially they go wrong, and then also how you can build your applications in a better way. So the biggest contributor was, well, data that had no apparent structure, right? So it was username or maybe like a language or something like this. And we saw this on 214 domains. And essentially this is just an example that we see here. So we get like the previous URL from local storage. So this is meant to show a backlink to the previous page. And assuming that this is under control of the attacker here, the local storage value, I can obviously inject something here in this last URL parameter and then have an exploit. And now you might wonder, but wait, there's no local storage is being accessed and it's being overwritten, so this would not be persistent, right? This would be a single shot. The thing is, if I already have JavaScript code execution, it's very easy for me to just hook assigning properties of local storage, and if it's the value that I don't want to have overwritten, I'll just say, yeah, sure, this was saved, this is fine, but keep my malicious payload in there. So we're really persistent here in this case. And as you might know, this is kind of the most common case that you see also for XSS, where you have a username and somebody injects HTML, or you're using this username in JavaScript and somebody breaks out of the JavaScript. And therefore there's existing solutions, and one of them is actually DOM Purify. So what you would like to do here is really have some context-aware sanitization, and in this case, if you think about it, what you would like to have is, well, you would like to have an href that is a URL and an HTTPS URL, right? So it shouldn't be JavaScript, it shouldn't have an on-click, it shouldn't have an on-event, on other events, and so on. So essentially, DOM Purify takes care of that for you, being aware of the context and just making sure that this anchor element does not have anything that could maliciously execute code. So it's that simple of a solution if you compare it to the last one, really just this one thing in between. And it's important that we use something like this and not just say, we can just use inner text, because then we would break functionality, right? Because we want to write a link here, so we cannot use inner text. All right, so the second thing that we saw a lot is JSON or JavaScript-like objects. So I'm sure that you all know that eval is a really bad idea, security-wise. Functionality-wise, eval is great. If you stick a well-formatted JSON into eval, you'll get the proper object out of it. If you take something that closely resembles JSON, but doesn't use double ticks, but single ticks for delimiting, that is technically not valid JSON, so you need to have double quotes. And JSON parse will tell you, no, this is not JSON. Okay? So if you have, for example, a server-side framework that initially generates this JSON with single ticks, then JSON parse will not work. So that's why it makes sense, if you want to say it like this, to actually use eval here. And so that's what's happening, right? So we have local storage visitor info here. We are evaluating this, so to essentially deserialize this value, and then increase here the number of page hits, and then write it back again. And so in this case, and you might think this is like a made-up example, it's inspired by real-world things that we saw. So people actually did this, and then in the end used JSON stringify. So well, the answer is really that simple. I'm not sure if you saw the transition here. It's like, replace eval with JSON parse, right? So this works well for anything that has been properly generated from JavaScript or a proper JSON library. So if you find these occurrences in your website, then just go the easy way and make sure that it's JSON that is in there, not some weird JavaScript objects. And in general, well, don't make use of eval. But I think that's not, especially not with something that could be controlled by an attacker. But then it's somewhat obvious. Code caching. That was also one of the things that surprised us a lot. So people were trying to, especially third parties, were trying to make sure that their scripts were loaded quickly. So essentially what they would do is, on the first time that you downloaded the script, the content of the script would be written to local storage. And then if you visit the page again, this code is executed. So they first get the library code, which is stored locally, evaluate that, and then once the page is loaded, they have all the time in the world to update the library. Okay? And so again, same issue as we saw before. As an attacker, I can still make sure that local storage is not overwritten. So once I have a persistent foothold in there, even if the library tries to override the local storage value, I can control that and just make sure that nothing gets overwritten. And this very clearly shows one problem where people think, okay, I write something into local storage and nobody will be able to tamper with this. And clearly, as we've seen in our examples here, this is not the case. And also, if you think about the thing that Marius said about the network attacker, right? So you might, for example, not, if you are here in a public Wi-Fi, you might not do certain, well, dangerous things, right? So you say, okay, now this is an untrusted network. So what I will do is, I will not log into Facebook, right? This is dangerous. Somebody could be tampering with me. However, if we manage to infect your machine here and you go home, you feel very safe, right? And if then all of a sudden our code is being executed here from local storage, you are going to be screwed at home and didn't even know when you got infected in the first place. All right. So what's the solution? Well, one solution is don't do that. If you want to do that, and there might be good reasons, if you want to consider that real-time bidding for ads is a good reason, then that's one reason where we mostly saw this, where you want, as the ad company, to be loaded very quickly so you can do your real-time bidding. You can just use, well, best practices in terms of cryptographic signatures. And this is actually inspired also by a fix to a problem, because we also, well, we at least tried to reach out to people that were affected, and the library providers. Not all of them responded or I think understood what we wanted to tell them. But this is actually what one provider did. So essentially they now have in local storage this lib code. They split the lib code, by the first new line, right? And so then the first line of the code now is a cryptographic signature over the rest of the code, okay? And then they just do this verification here. So verify signature, they have some public key, the signature and the code, and only if that holds true, then they will execute the code, okay? So even if, as an attacker, I manage to compromise the storage, nothing is ever going to happen because I cannot generate a valid signature for that particular piece of code. The alternative, which is actually better in terms of isolation, is actually service workers. So I'm not sure who of you has already worked with service workers. They are kind of a background task, more or less, that is able to intercept network requests. And also, in particularly, it's meant to be used for offline applications. And so what you can do in this case is, in the service worker, just add this event listener for a fetch event. So if I'm trying to get a resource, and effectively see, do I have that resource cached? And if so, then just deliver that directly, right? So it's really the service worker and not the actual server. And then again, in the background, because this is running all the time, you can do your updates, you can fetch the library again and have it, the current version cached. So this is really nice. In particular, because service workers are isolated from the page itself. So even if the page says I want to run the service worker, there's no way for the page to script into the service worker. So if you have an XSS in the page, nothing is going to happen. With one exception, I told you before, IndexedDB is shared between the service worker and the main page. So if the service worker uses IndexedDB for code caching, then it's again stupid, because then it's scriptable, or somebody can script into it again. The final thing that we saw is host names, or configuration information. So as Marius said, this is somewhat client-side load balancing, right? So you, when the client first visits your page, you randomly select one of your CDN servers to be the host for all the scripts, and then that will be persisted on the client here. But obviously, if I'm in control as the attacker of the host here, I have control from where the script is included, and again, this is going to be my attacker's website in this case. And so we looked at these particular cases, and it turns out that in virtually all cases, this was a subdomain of a common host name. Okay, so it was cdn1.ad.com, cdn2.ad.com. So the very trivial solution is actually just have a whitelist. Just make sure that it's either in a fixed whitelist of hosts, or make sure that the suffix is from ad.com, right? And then if you make sure that this happens, then even if as the attacker I'm able to control the this value in local storage or in the cookies, nothing can happen because I won't bypass the whitelist check. All right. Okay, so let me give you a bit of a conclusion here, and then share some somewhat exciting news that you already spoiled out a little bit, but it's fine. So persistent XSS, I hope we have first shown you that you should not just say there's DOM XSS. Okay, there is reflected and persistent client-side cross-site scripting, and as Marius showed you, also with the demo that we had, if you have a one-time infection, be it by a network attacker or by a web attacker, your application might be screwed for a very long time. And importantly, you as the developer of the site, you won't even know, right? Because it's not your database on your machine. It's on your client's or on your user's machine. We did this empirical study again. We're academics, so we have to do empirical studies a lot. And we saw that of the about 2,000 of the 5,000 sites that we looked at, sites that made use of local storage or cookies, 418 or 22% are actually exploitable. And depending on the type of attacker model that we consider, we either have about 300 or 65 sites that are susceptible to this end-to-end exploitation that Marius showed you. And even this trivially stupid way of looking at LinuxDB, really just like, does it look like JavaScript code? Let's replace it with an alert 1, right? Allowed us to find 60 sites that are vulnerable. So if you want to, next time you look at your own website, or if you're working as a consultant or pen tester, look at a company's website, please do have a look at these things and see if there's trivially JavaScript or HTML in there, because it's very obvious to see. And then for all the people that have been going to this conferences a while, I've been also here for a while, and I've been talking in previous years a lot about our ways to automatically find reflected clients at XSS. So we had this awesome taint engine that would allow you to track all these data flows from a source to a sink, and then even on top of that, add this exploit generation that Marius was talking about. And for a very long time, there was an issue of us not making that engine available. I don't want to go into the legal reasons for why that is. I can just say we have agreed upon that we don't care about the legal reasons anymore at this point. So it's been a while, it has been running. So actually last night I uploaded to that particular GitHub repository our taint engine, which allows you to visit a website and then just have all the data flows coming from all the sources that we discussed here, including also location href and so on, that go into things like document write, eval, etc. So you can run that yourself. There's one caveat. This is an engine from 2014. There's known bugs in Chrome from that period. So don't run it as root on your machine and visit just arbitrary websites, okay? If you want to play around with it, feel free to do so. We've also, as I said, made the exploit generator available, so the data flows that this engine can collect, you can just stick into the exploit generator and we'll return a URL that you can visit to, well, try and exploit the site. Obviously only your own or those ones that you are assigned to test. And finally, don't trust the locals, right? So don't assume that the integrity within your clients or your customer's web browser cannot be tampered with. And I think we have shown this. And at this point, we'd like to thank you very much for your attention. And if you have any questions, feel free to ask them. Huh? No questions.
If you don't ask questions, Ben will make some stupid jokes, and you don't want that. Don't quote me on that.
Hi, great talk. Is it safe to extend this topic to don't trust global storage or global variables or something like that? Since they can be accessed by XSS as well, right?
So, I mean, we have the issue of DOM globbering, right? And that has also been known. I'm not in too much details on how this is still a hot topic in today's browsers, because I've had a look at this like a couple of months ago, and things were a lot different than the results that were like back then. I don't even know when DOM globbering was really like shown to be around. But so I guess you should really question the integrity of a lot of things in your applications and don't take it for granted. So at some point it's really better to ask questions and put in defense mechanisms in depth rather than to just blindly trust the integrity of the web application.
And just one thing I want to add, also going back to the previous talk where we talked about well, event handlers and the way that you can use them with CSP. Essentially, I could also think of a situation where as the attacker, I'd not inject like a script alert 1 anymore, but I would just inject a particular piece of, well, properly formatted HTML. And I think there was a talk on script gadgets, I think also last year here, from Sebastian de Kies and other guys from Google. And essentially, there are situations where you don't even have to inject like markup anymore that directly executes, but you modify the context of the page by either injecting some some HTML or some Angular, well, markup or something entirely different, and then all of a sudden gets executed. And so it's not even that I have to check, hey, is my code that is using stuff from local storage, does it not just blindly eval it, but I also need to consider what would happen if now all of a sudden the structure of my page would be changed, and maybe there would be an element with some identifier or whatever, and now all of a sudden everything breaks. So I think in general, assuming that everything that is on the client can be tampered with should not be discounted. I think obviously if, as Marius said, there's always going to be an XSS, and in this case we just need a single shot, right? And once we have that single shot, your page might be, or your customers might be screwed for a very long time.
There's also one thing which I want to mention. There's one thing which you can actually do, which is a header that you can send, which just eradicates all client-side storages and also kills all running JavaScript execution contexts, which is called clear site data. So if you suspect something like this happening, just put it out there and clear all the storages of all your users once, and then you should be, then you can be certain that at least if your users have visited the site, have gotten the header, that the storages are like integer again. Thank you.